Adsorption. A mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. Adsorption may be classified as physical adsorption due to van der Waals forces, weak bending, reversible exothermic, or chemical adsorption, chemical bonding by reaction, usually irreversible exothermic. Terminology: adsorbent, substance with an interface where the adsorption occurs. Adsorbate, substance trapped in the interface. Adsorptive, gas or liquid compound that can adsorn at the interface of the solid. Adsorption process. Adsorbents used for wastewater treatment. Activated carbon, commonly used adsorbent. Other adsorbents, natural or synthetic zeolites, natural clay minerals, silica gel, and activated aluminum, silicic acid. Activated carbon, most commonly used adsorbent and is particularly suited to the removal of refractory organics. There are two types: powdered activated carbon and granulated activated carbon. Powdered activated carbon. Powdered activated carbon is fed to the raw water in a slurry or powder and is generally used to remove taste and odor causing substances or to provide some removal of synthetic organic chemicals. Advantages and disadvantages of powdered activated carbon. The advantage of powdered activated carbon is that the capital equipment is relatively inexpensive and it can be used on an as-needed basis. The disadvantage is that the adsorption is often incomplete. Sometimes even doses of 50 mg per liter are not sufficient. Granulated activated carbon. Granulated activated carbon is added to the existing filter system by replacing the anthracite with granulated activated carbon, or an additional contactor is built and is placed in the flow scheme after primary filtration. The design of the GAC contactor is very similar to a filter box, although deeper. GAC has proposed to be used to remove naturally occurring organic matter. GAC will typically last for only 90 to 120 days until it loses its adsorbent capacity, hence it is regenerated. Membranes. A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the case of water treatment, the driving force is applied by using a high-pressure pump and the membrane type is selected based on the constituents to be removed. In the membrane process, the feed stream is divided into two streams, the concentrate or eject stream and the permeate or product stream as shown in the figure below. Figure 6.43 shows schematic representation of a membrane process. The membrane is at the heart of every membrane process and can be considered a barrier between the feed and product water that does not allow certain contaminants to pass, as represented by figure 6.44. Membrane. There is a pressure drop across the membrane, called the transmembrane pressure, that must be overcome by the water feed pump. The performance or efficiency of a given membrane is determined by its selectivity and the applied flow. The efficiency is called the flux and is defined as the volume flowing through the membrane per unit area and time. The selectivity of a membrane toward a mixture is expressed by its retention and is given by membranes can be described by a variety of criteria including membrane pore size, molecular weight cutoff, membrane material and geometry, targeted materials to be removed, type of water quality to be treated, and/or treated water quality. Along with these criteria, membrane processes can also be categorized broadly into pressure-driven and electrically driven processes. Pressure-driven membrane process. Reverse osmosis. This process has traditionally been employed for the removal of salts from brackish water and seawater. It depends upon applying high pressures across the membrane in order to overcome the osmotic pressure differential between the saline feed and product waters. Reverse osmosis flow. Nanofiltration. This process, also called membrane softening, lies between RO and ultrafiltration. This membrane process employs 500 to 1000 kPa for operation. While it provides removal of ions contributing to hardness, the technology is also very effective for removal of color and DBP precursors. Ultrafiltration. Ultrafiltration membranes cover a wide range of MWCOs and pore sizes. Operational pressures range from 70 to 700 kPa depending on the application. Tight ultrafiltration membranes may be employed for removal of some organic materials from fresh water, while the objective of loose membranes is primarily for liquid-solid separation. Microfiltration. A major difference between microfiltration and loose ultrafiltration is membrane pore size. The pores of microfiltration are approximately an order of magnitude greater than those of ultrafiltration. The primary application for this membrane process is particulate and microbial removal. That's all. Thank you.